Welcome back. In our last video, we were talking about tokenization, where we took a text and generated tokens out of those. This is what it looks like. I found this example tick token where you can pass in a model, and for that model, it will generate tokens. In this case, 2 is the start of the text, and 8720 is Gen, 11716 is AI, and similarly onwards. So what tokens are doing is converting this text value into numbers that can now be fed into machine learning models. And these numbers are generated by the model itself. They have a pre-processing layer in there to generate these tokens. And these tokens are how these models learn. So in this case, you see Gemini has a mini in here. So Gemma, the way that's embedding the models, embedding the text is if you do a lowercase Gemini, then mini has its own token versus if you do capital Gemini, has its own token. So you will see this happen quite often where the words and how the tokenization happens determines how good or uniquely different the model is between one model versus another. You will see fail cases based upon how they are embedding tokens in here. But today we are not talking about token, mostly because when you look at tokens, tokens are encapsulating the word into a number, but they don't encapsulate any meaning behind the word. So how do you get all the meaning? So in this case, Gen and AI are 8720 and 11716, but the meaning behind Gen AI is more complex than just that. So how do you get the meaning behind it? And the way to encapsulate that into a form that model can understand is embedding. So that's what we're going to be exploring today, embeddings. Okay, so how do you get started with embeddings? We have the same setup as previously, where you get your key, you set up your SDK, you configure the key in there to be used by the SDK, and then you can start getting the embeddings in here. So we have the text Gemini, and we are going to be embedding that. And the model that we are using is text embedding 04. This will just generate the embedding, and we can see we have only printed first 100 characters of the embedding, and these are different values. So as we see right here is these values are not the same as this number here for Gemini 86303. It actually is multiple different numbers. So one way to think about this is it's a n-dimensional space in which these numbers represent where is Gemini in that n dimensions, like a point in that n-dimensional space. What is that dimension? What is that n dimension space? So in this case, it's 768 different dimensions on which we have embedded the word Gemini. And this is the embedding of that. How do you start thinking about tokens versus embeddings? So the way I like to think about it is discrete unit of text are tokens and embeddings are continuous numerical vectors of whatever you're trying to represent. So in this case, cat was 4991, but the embeddings for that is multiple vectors which represent cat in that n-dimensional space. And the best way to think about this is tokens are breaking down text into smaller units versus embeddings are trying to capture the relationship in the text. So an embedding for a whole word here is Gemini is 768 dimensions. You will also see a complete sentence in here might be represented in the same dimension space and so on. So another way to think about this is tokens are the individual words in a book, while embeddings are the underlying meaning and the story that is being conveyed by these words. My bad on the typo here. Okay, so this is well and good, but it's not really good way to look at it. So let's find a good way to look at it. This is MNIST dataset where it's a dataset of handwritten words. This was used quite a lot to recognize the words from the text itself. And here is an embedding view of those words where we have selected the MNIST with images dataset in here, and then we ran 630 iterations on it to build this dimensional graph. So what we're looking at right now is different dimensions, different values in here of numbers in different clusters. So this is representing that I don't know exactly how many dimensions are in this data set, but those n dimensions into a three-dimensional data set. So you see the three axes in here by red, green, and blue. And those three axes, and our data is being represented on those three axes. So we see here, all the ones are clustered here. We see sevens clustered here. Oh, I zoomed in. Sevens are clustered here. You see 6 and 5s are clustered back there. Zeros are clustered here. 2s are clustered here. We can also see that 2s and 1s and 7 have some relationship, and that's why they are clustered closer by to each other. You see the ones that look like 7 are clustered closer. There are some 9s in the 7s as well. So you see 9 and 7 in here, like 7s and 9s here. They are fairly close together because they look very similar. I remember seeing another one where 8s, 3s, and 5. So look at this, 5 and 8 and 3. Since they are similar, they are all clustered together in one area, and you can see the unique ways of writing 5 over here different than unique ways of writing 8 over here, versus in here things are meshing up with 3s as well. So what it's doing is it's capturing the meaning behind these characters, and in this case images. These are images of the handwritten characters. So it found the meaning behind those, and based upon that it did this whole putting them into different places onto this three-dimensional space. Okay, moving on back to the embeddings. So what else can you do with embeddings? In this case, we have batch embeddings. So you can take in a lot of text and generate multiple embeddings of those, so you don't have to make one API call per text value that you're trying to embed. You can also reduce the dimensionality of the embedding. So all of these are 768, but you can set the dimensionality to be whatever you want. We puny humans can only look at 3 dimensions. So I try to output the, in this case, truncate the embeddings to just 3 dimensions. And this is what it would look like in the 3 dimensions. Note that as you reduce the dimensionality, it will lose the specificity of the meaning that it's trying to convey. So often the meanings might get mangled. I reduced it from 768 to 3, so probably it's going to be really bad. But you can do that, and you might be able to figure out ways around where you reduce the number of embeddings, and based upon that increase your performance of generation as well as other things that you might be using embeddings for. Then you can also, on Gemini API, you can also specify different task types for the embeddings. So this is by default query type. You can also do it for document. If you're using embeddings for similarity, so back to this example, you could say a user inputs the word 6, and you're trying to find out similarity between the 6 and anything else. So you could find similarity between 6 and 1, which is going to be really bad, versus similarity between 6 and 9 in this case is going to be high, or 6 and zeros in this case is going to be really high. So that's what you could use embeddings for as well, where the task type is similarity classification. You could generate, using previous data, you can generate these embeddings. And when the new text comes in, you generate an embedding for that, and you try to find out, okay, this new word lies here, what is the closest value to it? And you can compute similarity based upon how close it is to other items in the list. Or you can classify that. I think the similarity and classification are similar topics, but depends on how you're using that. And similarly, clustering as well. So you can just take in a lot of input and pass all of them into embeddings and then generate unique clusters out of that as well. Of course, you can use it for question answering and fact verification as well. What does it actually do? So in this case, I generated one same text, hello world, different embeddings, different types of embeddings for all of those. Its dimension stays the same in 768 dimensions, but the embedding values themselves change. And this represents how optimized the embeddings are for these specific tasks. I actually would like to see more details from Google to be published around this topic, around how exactly does this API determine, and um, how does it define that, hey, when I'm doing fact verification, these should be the embeddings versus when I'm doing question answering. One result I found was interesting is the query embeddings looked very similar to clustering embeddings I see in here, but they might differ deeper into the text. I did not print more than 50 characters in here, so they might be different, but they looked very similar. So I'm very curious exactly how or what they are deciding internal to the model and exactly what is happening. If people know a research paper around that was published around that or anything around that, I would love to get my hands on it and take a read. Okay, so we generated embeddings. All of these are specific for text. As we see, our model is specific to text embedding in here on Gemini side. If you are interested in doing more other types of embeddings as well, you can look at VertexAI. VertexAI has multimodal embeddings as well, where you can use it for image classification, search, recommendations, and of course, you can use it for image, text, and video all together in one, for similarity, video content search, video classification, and stuff like that. That was all. Give it a try. Let me know how things go. And if you find a paper or any other documentation around how these task types determine the embeddings themselves or how the embeddings are generated, please let me know. And if you have any questions, I would love to answer questions for Vupil as well. So yeah, this was it. Thank you so much. See you next time.